My name is Jessica Enix, and I'm with the ACIL staff, and I would like to welcome you to today's presentation. Before we begin our presentation, I'd like to review a few points of protocol so that you'll get the most out of your webinar experience. Remember, you are listening to the webinar via a conference service. If you are disconnected, repeat the steps that were given to you by the registration email. In order to reduce background noise, please be aware that all participant lines will be muted throughout the presentation. If you have any questions, please type them in the chat box. A chat icon is located at the top right-hand side of your screen. Our presenter will address questions as they become available or at the conclusion of the webinar. Please note that today's program is being recorded and will be available to view on the ACIL website at the end of the day today. Now it is my pleasure to introduce our presenter, Ms. Lee Marotta. Lee has been a gas chromatographer for over 30 years, starting at Exxon Corporate Research in 1988. Lee moved to PerkinElmer in 1992 as a product specialist and is currently a chromatography product line leader focusing on solutions for the petroleum and environmental industries. Ladies and gentlemen, please welcome Ms. Lee Marotta.
Thank you, Jessica, and thank you everyone for joining our webinar today. I apologize for rescheduling. Last week I got really sick, and I apologize again because I'm still a little bit congested, but didn't want to wait that long. So today we will be discussing optimized techniques for measuring the concentration of terpenes in air. I'd like to introduce my co-authors, Jamie Brown of Millipore Sigma Sapelco. Jamie did a lot of research, which I will be getting into this presentation. He designed a new thermal desorption tube specifically for terpene analysis, so it's an optimized recipe. Paul and Aaron of Eurofins EnviroWorks in Edmonton, Alberta, has been doing field sampling of terpenes for a while now and worked with Jamie in validating his new tube. So we'll get on with the presentation, and thank you, my co-authors, for all your contributions. We'll first discuss the need. Then we'll get into thermal desorption. So that is a sample introduction technique that is used. We'll overview some of the method development. We'll discuss the applications used in the new tubes thus far, and then quantitation. How much is there? So why is there a need? There are several needs. Some of them regulatory, some of them industrial hygiene focus, and some of them characterization. So people that industrial hygiene, workers exposure, that work in the greenhouse, is there any type of toxicological effect of being exposed daily to terpenes? And thermal desorption in tubes are really, really accurate means of determining this. Emissions into the community, are they going to be regulated? There are discussions on this, again, for human health. Then there's ozone precursor concerns. I will define what an ozone precursor is in a little bit. Especially British Columbia is starting to have these concerns. Terpene profiling. We taste more with our olfactory sense, so measuring the air is a perfect way of determining and profiling, component profiling and quantitation, what the person is experiencing. And growers can classify their product so that the person that wants to buy it not says, okay, no, I like the flavor in A better than the flavor in B. Also, it's a great way of telling when plants are distressed and doing terpene ratio profiling. It's also a non-invasive way of determining what characterization, what terpenes are in the product. instead of destroying the product. Also, testing other terpene sources. So our goal was to develop a new tube specifically for the analysis of terpenes from cannabis and hemp. And Jamie Brown is the father of this new tube. And also to provide the industry with applications on testing and applications on sampling. Where do we want to sample? There's so many different places that we could do this, and for different reasons as well. And I'm sure that's going to be growing as we move on. What is thermal desorption? It's a sample introduction technique. Tubes are used. One of the ways and that's what we are going to be discussing today. And so after we sample, then we use the sample introduction technique of thermal desorption to get the sample, the targets we are interested in, into the analytical system for measuring and qualification. So why use thermal desorption? We could collect a wide range of terpenes and a wide range of components. And it could be very selective. Depending on the recipe, we use the absorbents we use in the tube. They are reusable and they can be conditioned, but typically you don't need to condition them because with thermal desorption, if you have the correct tube recipe, you are essentially cleaning the tube as you're doing your desorption process. Our recoveries, especially with an optimized tube, are 99.9 plus percent. We don't have to use toxic solvents we use heat instead of solvents to remove the targets from the absorbent, which is perfect. We use methanol to prepare our standards a little bit, but that's the solvent use. It had now terpene concentration levels vary very much depending on where you're sampling, and thermal and tube sampling is really accommodates that type of diversity in concentration range. Easy to collect and very easy to ship samples to the laboratory. They're small, unlike canisters, and it's not expensive to ship as well. Some other environmental applications, you have indoor, outdoor stack monitoring. Soil gas is really important, especially when it becomes soil vapor intrusion into someone's house or commercial dwelling. Manufacturing gas sites, there are Superfund sites around the country. New York DEP has an excellent explanation of these sites on their website. Uses thermal desorption. What's nice about thermal desorption is we're able to do volatile and semi-volatile components in one sampling procedure. So the boiling point target range goes from C2 and recovers up to C44. Ozone precursors I will get into on the next slide. Ozone precursors, this sampling from the EPA began with the Clean Air Act back in 1993. So I got this definition from Wikipedia. So ground level ozone is created by chemical reactions between NOx gases and hydrocarbons. The combination of these chemicals in the presence of sunlight form ozone. So the more we have these hydrocarbons, which terpenes is a hydrocarbon, the more ozone we're going to be creating, and we know ozone is a health concern. So this started back in '93. Like I said, PerkinElmer developed this method, and if you notice, if you're in a state that is in non-attainment or exceeds their allowable ozone precursor compounds, if you notice when you go to the gasoline pump, there's a recovery of the volatiles on the pump, and that was mandated by this act. So it's very important for health. So now let's dive into thermal desorption. PerkinElmer created and commercialized the first thermal desorber back in 1970, and we've had the pleasure to work on many many projects with the Environmental Protection Agency. Now, how does it work? So there are many ways to sample. In this instance, for terpenes, we have a tube and it is filled with adsorbents where the targets of interest will absorb onto the absorbents during the pumping process. We can also many times put sample in a tube to check for off-gassing at different temperatures. There's also canister sampling that could be done. Now that is taken right into the focusing trap. Or in the case of ozone precursors, we sample from a point, site point, so the instrument is on site. It's not like, so the sampling is done right onto the focusing trap instead of being desorbed from a tube onto the focusing trap. So in detail, and let's stick to the terpene application for now. We have a tube with our adsorbents. We put the tube on the canister. We could spike an internal standard, which is always good for validation of your sampling process, or you could automatically spike a surrogate on the tubes before sending them out to be sampled. Um, and this is automatic, a gaseous internal standard. It also does an impedance check. Sipelco or Millipore Sigma has been packing tubes in this business for, oh my goodness, from my memory. They are experts. It amazes me the repeatability on the back pressure from tube to tube to tube. Now, there's many reasons why that's important. But one of them is the back pressure. When you calibrate the tube for your flow rate when you sample, you only have to calibrate on one tube because the precision and quality control of the back pressure from tube to tube to tube is so perfect and excellent. And this is very time saving, but it also gives us better analytical results. The instrument will automatically do an impedance test to check this. So, and it'll give the person will set the allowances on impedance, and if that tube fails that back pressure, it will give the person a warning that that tube and what that impedance is. So you don't have to worry. You're validated throughout the entire process. It also does the packing for the terpene tube is very hydrophobic. So the water is actually being removed during the sampling process, but the instrument will also do we call it an ambient purge or a dry purge. It also rids the tube of any residual oxygen. Then the oven is placed on the tube, and with flow time, typical times for desorption is 8 minutes, but it's piggybacked with your GC runtime. And flow, the targets move out of the absorbent onto a focusing trap. Now, there's an inlet split before the trap for very contaminated samples. That inlet split is perfect, and I'm going to explain that and show that on, it protects the absorbents in the trap and protects the instrument from being overloaded. But I'll show that using an example later on during the application session. The cold trap, this is a schematic. We can choose to put absorbents in here. So we're using temperature and absorbents to focus the targets. The left side of the trap is narrow so that the chromatography comes into the analytical system in a narrow band, so you get nice peak shapes, which chromatographers love to have, better resolution. And as you can see, when the desorption of the trap occurs, we call this secondary desorption. The sample tube is primary desorption. We go in the opposite direction, and I'm going to explain that in a bit. Once we desorb the primary tube, we heat the trap at 99 degrees per second, so we get a nice narrow band. Here's an outlet split where we could, if we need to split more sample, or you could turn this off, split or splitless, or you can recollect that sample on a new tube or the same tube for later sampling if required. Most thermal desorption applications utilize mass spectrometry, except for the ozone precursor application, which uses a flame ionization detector. So we're talking about tubes. Let's get into the tubes. We have glass, metal, glass line metal, or deactivated metal. For field sampling, metal is desired because glass could break. Then also we could put more absorbent into a metal tube because it has thinner walls than a glass tube has thicker walls. And we could discuss probably tubes for 30 minutes, which we don't have, so that's just a little bit of a flavor for them. Now I want to discuss the recipe again. Jamie Brown optimized his tube recipe for the analysis of terpenes. The it's so flexible, thermal desorption. A lot of times you could get what you want, but omit what you don't want. There's many advantages, but let's talk about how it works. If you look at the inside of this tube, this is a 3-bed tube. Jamie's tube is a 2-bed tube. So we have a weak absorbent, middle range absorbent, and then a very strong absorbent. Let's say if we want to measure from 40 to boiling point of 4 components with the boiling point range from C3 to C40, let's just say. So the weak absorbent will retain the most heavy components, let's say to C20. Others will break through and go into the strong absorbent. Let's say this absorbent can retain from C20 to C6. From C6 minus will then break through that absorbent and be trapped and retained by the strongest absorbent. Now, when we desorb, well, when the instrument desorbs, we put the tube into the water sample carousel, so the flow is in the opposite direction as it's being heated, because we do not want to force the high molecular weight or high boiling point components into the strongest absorbent. This optimizes recovery, and that is why it's so important to use a recipe like the one Jamie designed to optimize this retention and optimize this desorption and recovery to get accurate results as well. Thermal desorption provides excellent retention and the mass spec, of course. This is an example of a TO17 run with the reporting limit as 0.05 part per billion or 50 ppt, with reporting limits in full scan, signal to noise in full scan, we could probably drop that another 10x. Now, I like to discuss the collection and analysis of terpenes using this new optimized sorbent tube, with a comparison to other tubes. And again, this is mostly Jamie's work. And Jamie went out to the field, and I think he had fun while he was doing this because I saw pictures. So here are the components of interest that we investigated. The shaded targets are the ones that were most prevalent and observed from cannabis and hemp. Here's an example of a real field sample. We looked at if there were any interferences. So Jamie here qualitative analysis of the beginning of this chromatogram where most of the volatiles came out. The first diluting terpene is alpha pinene. Here it is. And so most of the interferences chromatographically came before the terpene started to chromatograph. So we worked out the chromatography, optimized the chromatography. Here is just a run. It's about 19 minutes with the separation of the terpenes shown here. And if you notice here, the response factors look really the same, showing that from a standard, we're not getting discrimination. Typically, if we weren't desorbing hot enough or we weren't getting recovery, we would be getting discrimination against the high boilers, which means they would be lower in intensity. And this really is really, really cool that we are showing very, very good recoveries and retention of of alpha pinene in this run. So this really tells us a lot about our validation of the tube. We compared a 10x tube to the new two bed carbon tube, and as you can see, 10x does not, at ambient sampling temperatures, does not do a good job. We're not retaining the lights as well. And Jamie took a 2 liter sample volume, and of course, if you take a 10 liter, if you're not getting retention at 2 liters, it's going to be worse at 10 liters, and it looks really, really good on the two bed tube. Humidity is a factor, especially if we're sampling in a humid environment like Houston, Texas in July. So why is humidity a concern? Well, humidity takes moisture takes space on the tube if it's going to be retained. And also it can quench in the mass spectrometer, it could quench if there's a lot of moisture around, it will quench the target intensity in the mass spectrometer. And if your standards don't have the same amount of moisture as your samples do, the results will be low because of this quenching effect. Since there was no moisture retained using the new tube, that we don't have to spike moisture onto our standards because there was no moisture gained. This again validates our accuracy of our results. And also, we don't have to do a dry purge like sampling soil gas because there is a little bit of polarity in one of the absorbents. We need to do a dry purge. So we get to our split flows. So this was taken from a highly concentrated terpene area. And the first example was a split of 9-1, the second 102-1. So we could tell just from the smelling the area we're sampling in if that's going to be high or low. It's always better to take a low concentration as well, a low volume as well as a normal volume and run that one first. However, what's really nice about this is you could use your same calibration curve. So let's say it's like a dilution factor. Let's say we split none on the standards and we're splitting 10-1 on the samples. It would be a multiplier. So it would be like a dilution. So the software, you would just put a multiplier in the multiplier column in your software, and it will automatically um, multiply that by 10. Here are some of optimized conditions for thermal desorption, the analytical column, and also tuning. Mass spec conditions. Sorry. Now we'll dive into some of the applications that Jamie and Paul helped with, Paul and Aaron. So we see sampling in a greenhouse, sampling in the field, sampling in the laboratory from the ground material, and sampling of non-ground material from the headspace after equilibrium is met. I discussed calibrating the pump from one of the tubes, and here are just some of the ways that this is done. Of course, the flow meter is, in my opinion, the most accurate, but as long as the calibrators are calibrated, we're doing okay. And they're easier to use, of course, than a pump. Here is terpene profiling of the same plants at different growing stages. We thought this was an interesting experiment to take. 1 liter of sample, and we see an increase in myrcene air concentration from a mid-stage point in the growing process, and then comparing it to a later stage point. And it was, I think Jamie did a really good job of ratioing these results to alpha pinene. So we could look at this column and readily see what is increasing or decreasing during the growing process. This was samples collected in the hallway of a greenhouse. And what we did here, and this is done readily in thermal desorption to ensure we're not getting breakthrough, is taking 2 volumes from the same site. So the first volume was 1.22 liters, the second volume was 2.12 liters. If the difference between the different volumes is plus or minus 25%, excuse me for a second, we feel that we know we don't have breakthrough, and these results are excellent. Many of them were basically the same concentrations of, of, of the terpenes that we investigated. This is another way we could confirm that we're not getting breakthrough. This is not a terpene environment. Well, probably everything is a terpene environment. I mean, these trees in the background emit terpenes, so that was silly for me to say. In this example, we were looking at toxic components, though, and what we did here is we put a back tube. So the front tube is the primary tube, and the back tube is run as a blank before it leaves the laboratory. And then when it comes back, we can determine if any of the terpenes transferred onto that back tube. Since Jamie did a lot of work at many different sampling volumes, we're only presenting some of this work. We have that data already. But if you wanted to be sure, you could do this once and be sure. But again, the work has been done, and we will share. This is an example of the new tube from a grow room and a trim room, just to see the difference in concentrations of the terpenes from these 2 rooms. Alpha pinene was greater in the trim room, but the beta myrcene was about the same between these 2 rooms. Limonene, which is essentially everywhere, did increase as well as these other targets, other terpenes in the trim room. Now we compared our 2-bed carbon tube to a single bed 10x tube, and again we lost the lights using 10x. This is an example, the Penn State, which is very close to where Sipelco lives, allowed us to do some sampling at their hemp fields, and we saw from real live samples some alpha pinene, beta myrcene, limonene, and beta usonine. I don't do a really good job of pronouncing terpene compounds. I apologize for that. Now let's move on to sampling ground hemp flowers. So in this example, on the left is the flower, then our grinder, then sampling from a bag using Sipelco's ATIS extraction system, and how we transfer those materials onto our thermal desorber tube. Grinder, not all grinders are the same. We really want a homogeneous sample, and we all know in the real world that could be a difficult, or I should say challenging event. So we found this grinder to be very successful in providing us that homogeneous sample. So this is a dynamic headspace of the ground plant material. Dynamic meaning we are we are not reaching an equilibrium. We are continuously getting the sample from taking the sample from the sample. And as we can see, these are three different hop samples, and the beta myrcene obviously was larger in this one. But this is just a comparison of different samples, so you could see the different flavor or terpene profile and pick which one you like. This is a when if you look at the picture, we just took a gas tight syringe, very easy, and we drew a 100 ml sample from this ground from these flowers. And here is our profile, very accurate profile. And again, it's not only what's there, it's and the amount that's there. A lot of these flavorings is the amount compared to each other. So let's say if thymine was greater than limonene, even though they're both present, we'd get a different profile. So the ratio of these to profiling the smell or the flavor is critical. Here's an example of the whole flower and without it being ground up, and comparing it to the flour ground up. And look at these results are pretty, these collaborate really well. So should we do any grinding? This is a very good experiment that folks can do to compare if you're losing anything when we grind it up. However, that is what the person will be experienced as well. So both pieces of information is extremely important when profiling. Now I like to get into some of the work of the validation that my friends up in Edmonton, Alberta at Eurofins EnviroWorks did. We again, Paul and Aaron tested samples from the same site and did even more work on these samples. And this is just their calibration range, which relates to essentially a part per billion concentration in a 1 liter volume sample. To give you a lot of times when we do our calibration curve, we do it in nanograms spiked on tube, and then we depending on our sample volume, we put that in our, you know, we could actually put the concentration in the curve or whichever way you want to deal with it. The correlation coefficients are excellent and the precision looks excellent. We will look at Seadrill to find out why it became 8%, even though that's good, but we may have some integration interferences that we probably should look at there. So in summary, and thanks again for participating, we met our goal. The tube bed new TD tube is hydrophobic. As we discussed the benefits of that, it could be used for low concentrations and high concentrations. We've been sampling to 1 to 2 liters, seem to be adequate for inside the greenhouse. I'm sorry, my phone is ringing. Tubes are reusable, no toxic solvents, so it's environmentally friendly. And using thermal desorption, we're preventing the non-volatile components from entering our analytical system. So you will enjoy more uptime and less maintenance. So we'd like to acknowledge Christopher Simpson from the University of Washington, Francesco from Penn State, and Paul and Arifin, thank you so much from Eurofins EnviroWorks. And since I've been saying Jamie's name so much, I wanted to show a picture of Jamie, and Jamie is on the right in this picture. So Jessica, and here's our contact information. Jessica, I'd like to open it up for questions.